In this lesson, we begin discussion of an important reaction known as dehydration of alcohols. So we previously discussed that alcohols can undergo nucleophilic substitution if the OH is protonated to make it a good leaving group. Okay, that was a major theme. So if the acid used for protonation is HX, where X is a halogen, then dissociation of the acid generates H+, which protonates the alcohol, and X-. And X- serves as the nucleophile to give an alkyl halide as the product. So an example of this that we looked at is the reaction of terbutyl alcohol with HBr to give terbutyl bromide with water as the byproduct. That's great, but what if there are other strong acids other than the hydrogen halides? So what happens if an alcohol is treated with sulfuric acid or phosphoric acid? Now, to be honest, phosphoric acid is not a strong acid the way sulfuric acid is, but it is still capable of protonating an alcohol to some extent, and we will be able to see ourselves getting into the game with phosphoric acid too. Well, I think it's instructive at this point to look at the structures of these acids so you could understand a little bit about how they're going to react. So H2SO4 has 2 sulfur oxygen double bonds and 2 OHs, and H3PO4 has 1 phosphorus oxygen double bond and 3 OHs. In order to understand why substitution reactions are not going to happen when these acids are used, we've got to look at the structure of the conjugate base. So if you remove a hydrogen from sulfuric acid, you're left with the hydrogen sulfate anion. So it has a minus charge on one of the oxygens that was previously an OH. However, there are 2 additional resonance structures for this anion. So the minus charge is actually equally shared amongst 3 oxygens. There is no single oxygen that has very much of that minus charge, even half of that minus charge. Oxygens themselves are not particularly nucleophilic elements by virtue of their electronegativity. So the combination of the minus charge on oxygen and that minus charge being shared amongst 3 oxygens really makes this a crappy nucleophile. And dihydrogen phosphate is basically the same story, except there is only 1 additional resonance structure, because you could only use the electrons in the PO double bond when making additional resonance structures. Those 2 OHs bound to phosphorus have to stay there intact. If you were to try to put a minus charge on either of those 2 oxygens, you would end up having to move a hydrogen, which is not viable in drawing resonance structures. So incidentally, the fact that sulfuric acid is a much stronger acid than phosphoric acid is can partially be explained by the existence of an additional resonance structure to stabilize the anion. Okay, so these are clearly not good enough nucleophiles for SN2 substitution reactions. And while they may be good enough nucleophiles for SN1 substitution reactions, as we will see, there is something else that's going to happen faster in this case. So if there are any bases present that are strong enough for E1, then we must consider that E1 will compete, as we saw in the previous lesson, under SN1 conditions. Okay, so let's consider the reaction of terbutyl alcohol with sulfuric acid from a mechanistic perspective. I'm not going to give you the product yet. We're just going to take the starting material, react these 2 together, and start working our way through the mechanism. So step 1 is going to be protonation of the alcohol to make a good leaving group. And then step 2 is going to be loss of that leaving group to generate a carbocation. This should all look familiar. We have seen these 2 steps in a previous lesson when we looked at the SN1 reactivity of terbutyl alcohol with acid. We get to the carbocation the same way. So now, let's take stock of everything that we have in solution. In addition to our carbocation, we now have HSO4 minus that was generated in the first step as the conjugate base of sulfuric acid. And then we also have H2O present that was lost as a leaving group in step 2. Okay, so that means we have both of these present as possible bases or nucleophiles. So what are the possible fates of this carbocation? Well, first of all, HSO4 minus can act as a nucleophile for SN1 substitution. HSO4 minus can act as a base for E1 elimination. H2O can act as a nucleophile for SN1 substitution. H2O can act as a base for E1 elimination. So let's consider each of these possibilities in turn and evaluate whether we think that this will be the route chosen by the carbocation. So for possibility 1, the verdict is that it is possible. Okay? So the HSO4 minus is a pretty crappy nucleophile, as we said, but SN1 doesn't require a good nucleophile. You still have an oxygen with a lone pair. Can you get an SN1 reaction? Yeah, you can. But let's see if there's a better option. Remember, when you have two competing pathways, the product that you will get is going to come from the pathway that goes the fastest. And this one's just not going to be super fast. If there's nothing else to do, okay, but as we'll see, there is a better option. Is that option number 2? HSO4 minus acts as a base? No. That's impossible. HSO4 minus is too weak of a base for E1 elimination. It is a weaker base than H2O. Can H2O act as a nucleophile towards the carbocation? That is most definitely possible. But if you think about this, in step 2 of the mechanism, we just kicked off H2O as a leaving group. Can that leaving group come back? Yes. But that takes step 2 in the reverse direction. And then presumably, from the protonated alcohol intermediate, you could lose a proton and go back to the alcohol starting material. So can this happen? Yes. Does this happen? Yes. I'm almost certain that it happens. You can go from the carbocation back to the alcohol. Will we be able to see anything as a result of this process happening? No. It happens, it goes back to starting material, alcohol reacts, goes back to the carbocation. So essentially both of the first 2 steps can be thought of as being reversible. We've got one more option left. That better be the good one. And it is. H2O acts as a base for E1 elimination. Is H2O a strong enough base for E1? Yes. And if we do E1 elimination, that process under these conditions will essentially be irreversible. So that's what's the pathway that's going to be favored by Le Chatelier's principle. So let's continue with the E1 elimination mechanism using water as the base. So step 3 now will be removal of a beta hydrogen to generate an alkene. And notice you need an arrow going from the oxygen of the water to the beta hydrogen, and then another arrow going from the beta carbon-hydrogen bond to forming the carbon-carbon double bond. And the byproduct of this reaction now, when you protonate water, is H3O+. So the net reaction is terbutyl alcohol reacts with sulfuric acid to give the alkene plus H3O+. So this reaction is called a dehydration because the elements H2O are lost from the alcohol. If you count atoms in the starting material and count atoms in the alkene product, you have lost 2 hydrogens and 1 oxygen. Now, technically, the water molecule that's come off, those 3 atoms did not start their life in the alcohol starting material, because one of those hydrogens started its life in the acid that was used to protonate the alcohol. And the hydrogen that is lost from the alcohol is lost in a separate step, in step 3. So you may be looking at this and saying, wait a minute, this reaction generates strong acid. It's generating H3O+. Why on earth would it happen? But what you have to remember for this particular reaction is that sulfuric acid, which is your starting acid, is even stronger than H3O+. So when you use sulfuric acid as the acid, this process is actually favorable from purely acid-base reasons. So thirdly, you must remember that the base in step 3 is H2O. I don't know how many students over the years I've taught this class try to propose OH- as the base in this step. This reaction is taking place under acidic conditions. What that means is that H2O is the strongest base that can exist. If you had any OH- present in the presence of sulfuric acid, they would immediately react to give water and HSO4-. This final point is so important I put it in bold. Favorable acid-base reactions are faster than any other reaction in organic chemistry. So any OH- that may be generated in a minuscule amount under strongly acidic conditions will immediately react to give H2O. So if you're under acidic conditions, when you have acid present and your intermediates have positive charges, you always want to make sure that you never use OH- as a base, because it will not exist. In certain other reactions later on in the semester, there will be the opportunity to carry them out under basic conditions. For reactions being carried out under basic conditions, you're never going to use H+ or H3O+ or anything like that. The strongest acid present under basic conditions is H2O, and under basic conditions, molecules will have a negative charge. But I'm not going to say anything more about that right now, because basic conditions are not appropriate for the dehydration mechanism. The dehydration mechanism is under acidic conditions. Water is the strongest base, and all intermediates are going to have positive charges. Okay, so that's a nice, good dehydration mechanism for a tertiary alcohol. In the next lesson, we will consider what happens if you try to subject a primary or secondary alcohol to dehydration conditions.